Greetings and welcome to the introduction to astronomy. In this lecture, we are going to talk about radio telescopes. Now, previously, we looked at optical telescopes and some of the different detectors used. Now we're going to start looking at different types of telescopes that can help us observe the universe at different wavelengths. So what is a radio telescope? Well, one of the advantages is that radio waves can penetrate the atmosphere so we can see them from the ground. This gives us a new view on the universe because we're now seeing things at a different wavelength than visible light. And that means some objects give off radio waves but are invisible in ordinary visible light. So it allows us to sometimes see objects that we could not otherwise see. One emphasis is that radio waves are not sound waves. You cannot listen to radio waves from space. Radio waves can be used to encode sound waves and to transfer sound through radio. However, they themselves are actually electromagnetic waves, just like light, just much longer wavelengths. Let's look at some of the beginnings of radio astronomy. It was the very first astronomy outside of visible light, beginning in the 1930s with Karl Jansky, who was looking at radio communications, and he found radio waves emanating from an unknown source. Now, the interesting thing is that they appeared 4 minutes earlier each day. Now, if you remember back to an earlier lecture, there is a 4 minute difference between the solar day, the cycle of the sun, and the sidereal day with the stars. This was the sidereal period of Earth, meaning that objects were coming up 4 minutes earlier each day, and they must be associated with something in the sky. And in fact, he was detecting the strongest radio source, which is the center of our galaxy. And we see a recreation of his very early model telescope here. Now, when we look at radio astronomy, what can we study? Well, actually, radio astronomy lets us study the two edges of the spectrum. We can look at very cool objects like molecular clouds, which are very cool, do not give off visible light, but do give off radio waves. However, we can also study highly energetic objects because the accelerated electrons will also give off radio waves. And we see that here with the Crab Nebula. And when I talk about being able to see things in get different views, the big image here is the main view of the Crab Nebula in visible light. However, it's different if we look at it in the radio. In fact, we see a concentration source at the center there. If we look at it in the infrared, structure looks somewhat similar. Ultraviolet is a little different, and X-ray really shows something interesting going on down at the center here. And those are things that we miss in the visible light image, not because we don't want to see them, but simply because that area is not giving off visible light in the same way that it is giving off radio waves. Now, why use radio astronomy? Here's one good reason, is getting another view on the universe. But let's look at some of the advantages and disadvantages of radio telescopes. One great advantage is observing 24/7. Daylight does not matter for radio waves. While the sky is bright in visible light during the day, it does not give off radio waves. So you can pretty much observe as long as you don't get too close to the sun, which is a radio source. Weather is not an issue unless you have either an incredibly dense blizzard or a thunderstorm. So the electrical discharges in a thunderstorm would cause interference in the radio equipment. But overall, light rain, light snow, you can observe right through that. You can observe through clouds. You don't need to worry about any of that. As we mentioned previously, it is a different view of the universe, which is important. Also, radio waves can penetrate dust, giving us a view of different parts of our galaxy. So we can see the galactic center in radio waves, but not in visible light. And that cool hydrogen gas, which is much of the universe, is something else that we can see in radio waves that we do not see in visible light. Now, some of the disadvantages are poor resolution. If you remember, the resolution depended on the size of the telescope. So you'd think very big telescopes would give you good resolution. Well, that wasn't the full picture. In reality, the resolution depends on the wavelength of the light you're observing and the size of the telescope. So a big telescope helps, but a long wavelength like radio waves hurts. So you need to make very large radio telescopes in order to be able to get decent resolution. You also get interference from radio signals on Earth. Just as we have light pollution with visible light, we have pollution with radio signals. So how can we get around some of this? Well, there are some ways, and we can use what is called interferometry. This increases the resolution of radio telescopes. What do you do? Well, instead of observing with just one telescope or making an extremely large telescope, you can use the same object observed with multiple telescopes and combine the signals together. This increases the effective size of telescopes to the distance between them. So here we're looking at the Very Large Array, or VLA, out in the desert of New Mexico. And it is a set of 27 of these telescopes, which are spread out. So instead of making one telescope kilometers in size, which would be very difficult, multiple telescopes that can look at the same object can give you the effective resolution of one telescope with the greatest distance between any two telescopes. And now we can match or exceed the resolution of optical telescopes. Now let's look at some famous radio telescopes. Here's one that doesn't look in too good condition. This is the 300-foot Green Bank telescope, which actually collapsed in 1988. And here we see the collapse image. The replacement was completed in 2000, about 12 years later, and that is the 100-meter Robert C. Byrd radio telescope. It is the largest fully steerable radio telescope that exists. And here is the updated new radio telescope that was built to replace the collapsed Green Bank. And again, it's the largest one that is fully steerable. Now, that doesn't mean it's the largest radio telescope, but this can actually be pointed at different directions in the sky. Note, 100 meters is about the size of a football field that you are steering here. So that is an incredible amount of engineering to be able to get something this massive and be able to point it across different positions in the sky. Now, there are some other telescopes. There was the 300 meter, 3 times larger than the Green Bank telescope. And that is the Arecibo telescope that was completed in 1963. Until 2016, it was the largest single dish, 300 meters across. And we now have another larger telescope, which is the FAST telescope in China, which is even larger, similar structure, but much larger, almost not quite twice as big. Now, what happened though with the Arecibo telescope is it did start a collapse in 2020, and that eventually led to its decommissioning. So here we see the video from one of the drones as to that collapse and as to what happened. It had started before this, but eventually everything just gave, and you'll see the whole piece here that will actually collapse down as the last piece gives, and the major detectors there collapsing in and actually destroying part of the dish. It was deemed to be unrepairable, so was therefore decommissioned and not going to continue, not going to be rebuilt, at least as that telescope. That whole telescope was gone. But it was great for over 50 years, was one of the very large telescopes in radio astronomy. Now let's look at what about the future of radio telescopes. Well, there are a couple things that are being worked on. There is the SKA, Square Kilometer Array, and that is projected to be completed in 2027. And what it is going to be a square kilometer of collecting area. So the telescopes actually spread over much larger areas. But overall, when you add the amount of collecting area, it will be 1 square kilometer. And this is currently scheduled for completion in 2027. Also being worked on is the NGVLA, the next generation VLA. And that is in planning. So it's very early stages, currently projected to be completed in 2035. But it's an updated version of that very large array, with again much more updated technology and better telescopes to be able to give us a better understanding of the radio emitting objects in the universe. So let's go ahead and finish up here with our summary. And what we looked at was radio waves are easy to observe from the surface of the Earth because they do penetrate the atmosphere and we can study them from the ground. They give us a different view of the universe. We see objects that emit radio waves that do not emit other types of electromagnetic radiation. And we talked a little bit about interferometry being used to increase the resolution of the radio telescopes. So that concludes this lecture on radio telescopes. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.